Software is absolutely everywhere. It's running our phones, our cars, our banks, pretty much our entire world. But if you've ever been part of a team trying to build it, you know it's just notoriously difficult, right? Projects are always late, they're over budget, and they're just full of bugs. So, why is building something that's made of pure logic so unbelievably hard? Well, today we're going to dive in and explore the incredible journey of programming, how it went from being this creative art form to a full blown engineering discipline.
Okay, so to really get a handle on this, think about it like this. Building a simple little piece of software, that's kind of like building a doghouse. You can probably just figure it out as you go. One person can do it, and hey, if you mess up, no big deal, it's pretty easy to fix. But building large, complex software, the kind of stuff that runs a global business, that's like building a skyscraper. You can't just wing it. You absolutely need blueprints, you need a highly coordinated team, and you have to rely on proven engineering principles. If you don't have those, you're not just going to have a few problems, you're pretty much guaranteed to fail.
Way back in the early days of computing, that doghouse approach was really the only way people knew. Programming was treated like this creative craft, almost like an art form. It definitely wasn't seen as an engineering discipline. But as our ambitions for what computers could do got bigger and bigger, this approach started to show some really serious cracks. This early method has a name. It's called exploratory programming, or to be a little more blunt, the build and fix style. You just jump right in, start hammering out code, and then you patch up the problems as they pop up. I mean, it's intuitive, right? It feels super productive. And for small, simple programs, it actually worked just fine. The problem was, this simple approach had a massive hidden flaw that was about to trigger an industry-wide crisis. Now, this is where things get really fascinating. Look at what was happening with the money. As computer hardware got exponentially cheaper and way more powerful through the 60s and 70s, the cost of software just started to skyrocket. It was a total reversal. We could build these massive machines, which meant we wanted to solve even bigger problems. But the cost of writing the code to actually do it was just spinning completely out of control. And this crazy imbalance led to what everyone started calling the software crisis. It was a huge deal. Projects weren't just a little late, they were constantly massively late. They blew past their budgets. The final products were notoriously unreliable. They'd crash all the time. And maybe worst of all, trying to maintain or even just update them was a total nightmare. The old build and fix method that worked for the small stuff was completely and utterly failing at scale. So what was really going on here? Was it just a bunch of messy code or bad programmers? Nope. As researchers started to dig in, they realized the real problem was something much, much more fundamental. Turns out it has everything to do with the built-in limitations of the human brain itself. And this brings us to the absolute core question of the whole software crisis. Why does the effort to build software seem to grow exponentially? Why isn't it linear? I mean, think about it. If you double the size of a project, you'd think it would just take double the work. But in reality, it often takes 4 or 8 or even 16 times the effort. What is going on here? The answer, it turns out, is in our cognitive wiring. See, psychologists make a distinction between our long-term memory and our short-term memory. And that short-term memory, that's our brain's RAM. It's the mental workspace we use for all of our active thinking and problem solving. And here's the crucial point. It is incredibly small. Just how small are we talking? Well, this is the magical number that the psychologist George Miller discovered. It turns out that, on average, a person can only hold about 7, plus or minus 2, unrelated things in their working memory at any one time. That's it. That is our entire mental bandwidth for juggling details. And this, right here, gets to the absolute heart of the problem for programmers. A really simple program might only have a few variables and functions you need to keep track of. Easy. But a complex system? It can have hundreds or even thousands of interacting parts. The second you have to mentally juggle more than about 7 of those details at once, you hit cognitive overload. Your brain literally can't keep track of it all, and that leads to confusion, forgotten details, and some very, very costly mistakes. So, if our own brains are the bottleneck, how in the world do we build these massive systems? Well, this is where software engineering rides in to save the day. It's not just a random collection of best practices. It's a whole discipline built around one core idea, creating methods to build complex stuff in spite of our natural cognitive limits. And it all boils down to 2 fundamental principles for taming that complexity. The first principle is decomposition. This is that classic divide and conquer strategy. You can't break a thick bundle of sticks all at once, right? But you can easily snap each one individually. It's the same idea here.
You take a massive, overwhelming problem and you just break it down into smaller, independent subproblems that are simple enough for a single person's brain to actually grasp and solve.
The second big principle is abstraction. And this is all about simplification. Think about a map of a country. A map is useful because it ignores all the irrelevant details, right? It doesn't show you every single tree or every single house. It just shows you what's important: the cities, the roads, the borders. Abstraction in software does the exact same thing. It lets us create simplified models of complex parts so we can think about them without getting completely bogged down in every tiny detail. So you put it all together, and it's like a superpower. Decomposition breaks the huge problem into manageable chunks that fit inside our 7 ± 2 mental limit. And then abstraction lets us think about those chunks in a really simple way. Together, these two principles are the absolute foundation for how teams of people can build things that are way too complex for any one person's brain to handle alone.
Now, these two core ideas, decomposition and abstraction, they weren't just a one-time fix. They really became the driving force behind decades of innovation in how we design software. They led to us creating better and better blueprints for building these huge, complex systems. And that evolution kind of looked like this. Back in the 60s, the big focus was on structuring the flow of control, trying to avoid that tangled spaghetti mess of go-to statements. Then in the 70s, the thinking shifted to organizing the data structures first. In the 80s, we saw the rise of data flow design, which was all about mapping how information moves through a system. And then from the 90s on, object-oriented design really took over, which cleverly bundles data and the functions that use it into these neat, reusable packages. You can see how each step was just a smarter, more sophisticated way of applying those same core principles, decomposition and abstraction.
Okay, so that's a lot of history. But why does any of this matter to us today? Well, because it represents a truly fundamental shift in mindset. It's all about moving away from just reacting to problems and toward a proactive, preventative way of building things. This engineering mindset is a huge deal. It means shifting from just correcting errors to actively preventing them from ever happening. It means recognizing that coding is just one small phase of the whole process, and that you have to start with super clear requirements and a solid design. Things like systematic testing and peer reviews became absolutely essential, not just nice-to-haves. And finally, creating high-quality documentation gives everyone visibility into the plan, so the whole team is on the same page. And here is the hard economic reality that really drove that whole shift home. It's been shown that an error found during the design phase might cost, say, $1 to fix. But that exact same error, if it's found by a customer after the product is released, could cost thousands of dollars to fix. It's just simple math. Prevention is always, always cheaper than the cure. So, to sum it all up, this whole journey from the software crisis to modern software development was really about one thing: transforming programming from this unpredictable, intuitive art into a reliable, scalable, and manageable engineering discipline. One that was built from the ground up to overcome the very real limits of the human mind. But, the evolution isn't over, not by a long shot. As we start to enter an era where AI can generate enormous amounts of code all on its own, it leaves us with a really fascinating question to think about. If the last 60 years were all about creating principles to help humans manage complexity, what will the next generation of software engineering principles look like when our main challenge is managing the complexity created by machines themselves? Definitely something to think about.